Hello, this is Dr. Ellert, and today we are going to get started with the 3D Modeling with Fusion 360 optional module for CEC 112. Today's learning objectives is for you to understand the importance of CAD in engineering, specifically in design, to describe the differences between parametric and non-parametric modeling approaches, to explain the differences between extrusions and revolutions in 3D modeling, explain the differences between fillets and chamfers in 3D modeling, and demonstrate your modeling knowledge in creating three-dimensional objects. So let's start with looking into the approach of engineering design and why this actually matters in the beginning. So if you recall, the traditional engineering design process has a list of numbered steps where you start with problem definition, develop a goal or objective statement, gather information and list out the different assumptions that you need to make, develop a solution, demonstrate that that solution will work or satisfy your objective, and if it doesn't, continue to iterate until it does not meet the objective, and then report and document your results. In 3D modeling and CAD software, much of what we are spending our time on is developing a solution and demonstrating that it satisfies our objective, and if not, iterating through that CAD program. Additionally, what we can do with that model in the demonstration of the solution satisfying your objective is then include that model in different simulation software to double check and make sure before we invest a lot of money in actually making a product that it'll actually work and perform the duties at hand. One of the most critical steps in the design process is coming up with developing and testing a solution. When you start with a general solution or your general ideas, you're going to start with just brainstorming ideas and likely with quick sketches or getting inspiration from other designs that you see across the board. And then you'll transition into build a specific model to scale for the solution that you think will best work. Historically, this was all done by hand. This was done on drafting tables in large ceiling or large rooms with skylights to allow for a lot of diffuse light, and this took a lot of time and effort. When something needed to be changed, it took a very long time for everyone to update each individual drawing and to make sure that each individual part that interfaced with each other were able to work based off of those changes. It was an onerous and difficult process. Now what we typically use is computer-aided design software or CAD software. This makes things a lot easier for a number of different reasons, but specifically because we now have digital files, and once a digital file gets updated, it can permeate and waterfall across all the different designs without as much difficulty. There are two main types of modeling approaches, parametric and non-parametric modeling. Non-parametric modeling is similar to sculpting with clay or some other malleable wire, some other malleable material, where you can push and pull and modify features independent of each other. This is done a lot in concept design. This is done a lot in just getting a visual look of the model, but doesn't necessarily help with the interrelatedness of multiple parts. Parametric modeling is used more often when you expect that there are going to be interrelated parts. It uses relationships between different features, and so as one feature changes, all of the other relationships will update changes on the other features. And that means that we can use formulas or embed different formulas instead of embedding specific numbers if we want to refer to one thing versus another, so we can scale and adjust and keep the relative dimensions the same while scaling and taking something from 1 centimeter to 1 millimeter or 1 millimeter to a meter amongst the board. We'll be using Autodesk 360 or Fusion 360. Specifically, that's been provided to us through the Autodesk environment. Autodesk has a collection of different modeling programs that have been specifically developed for different modeling or CAD needs, including Inventor, Fusion 360, Revit, and AutoCAD. In this class, as I said, we'll be using Fusion 360 as it's cloud-based and compatible with both PCs and Macs. Inventor is PC only, Revit is specific for building and building design. AutoCAD doesn't have as many features as we would like to have. So Fusion 360 is going to be the software that we use specifically in this class. And if you're an MME major, you'll learn modeling in more advanced classes in MME 201. And now you'll be learning NX, which is just provided by a different company, Siemens, instead of Autodesk. They look similar and will behave very similar ways. Most parametric modeling software, which is all the things that we've been talking about on this slide specifically, is very similar. So once you know one, you can learn another fairly easily. And that means that if you have a background in AutoCAD or Inventor or SolidWorks or another parametric modeling system, you will start seeing a lot of similarities between the background CAD software that you know and understand versus the CAD software that we'll be working on with Fusion 360. Before we get into modeling, I'm going to be using a number of different terms that are going to be important for you to understand what they are, and I'll show you where they're located and the buttons that they're located. And once you understand what each one of these values or each one of these things do, hopefully it'll make it easier for you to understand why we're incorporating them into our design. This is not all of the critical terminology, but these are the four main words that you'll see over and over again as we get into modeling our system. The first two words that I want to talk about are extrusions and revolutions. So the way that we mostly work in CAD is that we create a 2D sketch, and then we take that 2D and convert it into 3 dimensions by two different processes. Either an extrusion, where we are taking a shape, as you see down here in the lower left. We're taking a shape and we're literally taking that cross section and stretching it above or below or above and below in order to make a 3-dimensional object. This is very similar to when you played with Play-Doh and you pushed it through a die and you got a long thing that had the same cross-sectional shape as what the die looked like. That's the same sort of process. The other way that we can create an object is specifically more round and spherical objects is through a revolution, where we create a profile like you see here in kind of the middle, just off, just to the right of center. And we can create a profile, and then we can find an axis and revolve that profile around the axis as you see in this last image here. This is very similar to what you learned in calculus, where you take a shape and you revolve it around an axis, like you take a circle, revolve it around an axis and make a sphere, or revolve it around an axis and make a donut. It's the same sort of approach here. We can directly build 3D objects, but that is beyond the skill level that we expect students to have in this module and beyond the development that we'll be able to have time in class to work on. So a revolution and extrusion are the two main ways that we take a 2-dimensional sketch and turn it into a 3-dimensional object. The other thing that we need to think about is how our parts are going to interrelate with each other. And the two ways that we do that is through adding features. There are two common surface features that we use to make your design either better or easier to be manufactured, or easier to interface with each other. So if I want to design something and draw something with a 90-degree corner interfacing onto a 90-degree corner, this is near an exact 90 degrees is really near impossible to construct. It takes an incredible amount of effort, energy, time, and it's not usually worth that effort, energy, and time to be able to actually have a true 90 degrees and a true 90 degrees. So some of the ways in which we fix our model in order to make it easier to design is through the development of fillets, which are going to be rounded edges. This is what's called an external fillet. If I wanted to round this edge as well, that would be considered an internal fillet. But fillets have radii. They're usually defined by radii, and they round our corners. This helps them when we're manufacturing them. It helps them come out of a mold a little bit easier, and it also keeps us from having sharp corners. And When we have sharp corners, cracks can form at those sharp corners, so rounding them makes it easier for a part to last a really long time. The other way that we can modify our corners so that they're no longer as sharp is through what's called a chamfer, which is just cutting off the corner with a plane. Usually these chamfers are set to 45 and they're just cutting a square off of the plane like you see here. Again, it's used as a way to help materials interface with each other or parts interface with each other. It's used to help make it easier for us to machine different things. This makes our corners less aggressive. You can see that we have two obtuse angles instead of a 90-degree angle on this corner. So it makes it harder for cracks to form in this space, makes it easier for us to move this part in and out. These are critical features that are going to help us in the modeling side of things in order to ensure our parts fit better together. Fillets and chamfers, and you will see them significantly when we start building our parts. So with that, you have the basic terminology that we're going to use in modeling, and let's spend the time actually modeling the system that we're trying to model, which is a Rubik's Cube.